we're going now, and I will tell you a few words about oil in circulation. Let me come here so that I can, see the same thing as you can see. So, okay, I hope it will do a little bit better now. So, this is what I plan to tell you something about. And this is to talk about introduction, to tell you something about facilities, methods, what we have used in this particular project and approach, and some results. I'll give you a summary. Then what you see here on the top is annular mass flow of oil in a discharge of the compressor. I started this activity in oil flow in compressors several years ago, maybe 10 years ago. And I had several students who were working on that, basically mostly because of problems with CO2 compressors. At that time, some CO2 compressors used to have 10% oil in circulation rate. And then people from that company had asked me if I can help build some good separator for that for that CO2 compressor. And then I started asking myself first, what do we separate? And then I was asking them, when you build oil separator, what do you separate? Yes, we know there are some droplets, there is some film. How many of droplets are there? What is the size of a droplet? What is the velocity of a droplet? How much oil flows? What is the breakdown between oil flow and film flow? Do we want to separate film? Do we want to separate droplets? So first we had to look into what's flowing in the compressor discharge. Then I was asking almost everybody. Nobody was able to tell me what that is, or maybe that was very confidential information, but I didn't have information about it. Then I thought about, okay, how to visualize that? Then the problem in visualization is you always have a lot of oil inside. You can have a discharge and you will see. There will be a transparent discharge too. And in the end, we made a transparent compressor, discharge chamber of the compressor. So we can now see, and I will show you something about valves, but this is a separate presentation about flow of oil in the discharge chamber of the compressor. Then we had to develop a totally new technique. As you can see, this is how the flow looks like. This is what you see outside of the tube. These are here waves that we see from the bottom, and in behind you see some dark drops, and these are the droplets. So we had to develop a technique to quantify what is flowing inside. What is the thickness of the justice? Oh, this is very sensitive. Okay, I apologize. So this what you see here as these droplets. This is with high-speed camera video taken, and then these are the droplets of oil, and you see from time to time different sizes flowing by, and this is what I wanted to show with this picture. Basically, what we see here is a film, and this film, when the velocity is very low, is relatively smooth. As velocity is increasing, waves are formed. And what is happening? At the compressor, where is oil coming from? Oil is always coming from the compressor. That means all oil has to go through the valve. And I will show you a few videos from the valve itself, how that looks like. And you will see some droplets and some ligaments, some very long droplets, which will break into parts, and it will form sort of a misty flow. And that misty flow comes to the compressor discharge pipe. And this would be somewhere here. What happens then, I will show you later a video of that, all of these droplets start hitting stochastically hit left and right the wall of the inner discharge pipe, inner wall of a discharge pipe. And what happens then? These droplets stay inside and form this film. What that means? It means that there is no steady state at all in the discharge pipe, because at the beginning you have zero film thickness and all your oil flow is in mist, in droplet mode. As we move towards kind of exit along the pipe, more and more droplets are being absorbed here. This film is getting thicker and thicker. Waves start to form. Kelvin-Helmholtz instability here will form greater and greater films, and we will start having detachment of the oil from that film. Basically, this is the same like when you are at the sea, when you see first wave happen, and when you have a very strong shear, a lot of wind blowing over the waves, the crest of the wave will start sending droplets back again. So there must be a steady state point, some kind of balance point. And what was it? That is a different presentation. I'm just giving you some introduction into that to come to this part, because this is only one small portion of that story. And that typically is always the question, okay, now when I understand the physics less or more, I have some concept, what is the reality? Because if I want to build a compressor, if I want to build the separator, the question is then, how long is that? Typically, in the normal smaller compressors here, where discharge velocities are between 10 and maybe 20 meters per second, the size of a discharge pipe is appropriate for the flow rate. Typically takes between 1 meter and 2 meters to come to that equilibrium point. And of course, that equilibrium point is also a function of oil and circulation rate. If your compressor is made to have more oil for whatever reason, if it is a screw compressor, you want to inject oil, if you have a certain refrigerant in certain conditions, you have a more or less separation of oil in the compressor, we are typically shooting between 1 and 5% oil in circulation rate for that range. Between 0.5 and 1 is relatively good, and when you go to maybe 4 or 5, this is typical for automotive systems, because automotive compressors typically don't have a crankcase. That's also very important to have in mind, and OCRs are much higher. Then that length is something about a meter, meter and a half, where you get at between 3 and 5%, you come to equilibrium. Now, what I will try to talk today about is that same issue, but very often compressor manufacturers cannot measure easily oil in circulation rate. Why is that so? Because to measure oil in circulation rate, and I'll tell you that later, there are various methods to do that. Speed of sound, refractive index change, density change, and whatnot, or you can take a sample, but all of that has to be done at the liquid line. To get the liquid line, you have to close a circuit. That means you have a huge capacity, especially for industrial refrigeration compressor manufacturers. Like if you have something like 100 kilowatts to maybe 500 kilowatts, these pipes are big, capacities are huge, it is very expensive. So I was thinking, can we now here, with all of this that we have learned, make almost a way to measure oil in circulation rate optically? And then to tell you something about what is oil in circulation rate and what is oil retention at the compressor discharge. Okay, this is what I'm going to be talking today. That's my plan. Long introduction. But I hope that it is a little bit kind of easier to get the point when I now start going. Okay, first of all, what do we know about oil? there are two measurements, oil retention and oil in circulation ratio, OCR. So this here, OCR, is really how much oil flows compared to the total flow of refrigerant. Oil retention is related to that, but it is more how much oil is in the pipe. Why is that important? Because how much charge do you want to have? In heat exchangers, it reduces or it could increase sometimes heat transfer coefficients, but you typically want to make sure that you have enough oil to come back to the compressor. Okay, so oil retention is something that if we would be able to freeze this flow like this, how much mass here is inside, this is oil retention. And if you think about how much oil flows, that's oil in circulation ratio or rate. And here are the things. Oil retention, oil is retained in form of film and in form of droplets that are frozen in time here. Or OCR can also be how much oil is flowing with this in this film mode and how much in the droplet mode. Okay, I don't want now to say too much on these equations. Nobody likes equations in this type of presentations, but it is good to kind of at least show that this is not only a visualization, but this is also something really serious. So this is how we can calculate OCR, oil retention in the film, and contribution of that film to OCR, oil retention in droplets, OCR contributed by droplets, and the question is how can we measure that? Okay, putting these equations is relatively easy. Every student will be able to do that. The problem is how to get these numbers, these diameters, numbers, velocities. That is tough. Okay, we have here a facility just to show you that there is some facility with some heat exchangers here, and that this is real compressor. Here, this is Kroll, so-called 3 tons, 10 kilowatt, 11 kilowatt capacity at the normal conditions. And what we measure. Over here, you see, this compressor is, originally it was a normal compressor. Then we put the flange and put the side glasses. That wasn't enough. Then we have made here transparent chamber to be able to watch what is happening in the compressor discharge valve to see, and I'll show you some videos. And then this is a discharge tube, and this part of the tube here is transparent. We put here high-speed camera, put a light source, and then around we go and measure with this laser, we measure the thickness of the film. And with high-speed camera, we try to measure how much droplets, how much oil is in a droplet. That means how many droplets, what is their velocity, what is distribution, and so on. So I will then tell you something about oil film thickness and oil film velocity. So how do we measure oil film thickness? We have here a laser, and this is relatively inexpensive. Anybody can try that. This is self-developed method in my center. So here is the laser which is shining the light through transparent wall, and then we have reflection of the surface of the oil film, and it comes back. So what you see here is what is seen from the outside by the camera. So you see here, this is a laser, this white, and that laser pointer is the same laser pointer as I'm using now. This is nothing expensive. This is very, very cheap. And then this is when the film is thin. When film is thicker, this is what you see. When film gets even thicker, wow, this is very sensitive. So here, I have here 3 stages to show you, 1, 2, now, and 3. This is the largest. So as film gets thicker, the radius of that ellipse, the major axis, gets bigger and bigger. Now, by measuring this diameter, And you can get here the oil film thickness. Now, of course, you will get here some diameter, and you can make a model, but then, of course, you need to calibrate that. That is the tougher part. This is how have we done calibration. With the same camera, with a laser pointing, this is, we've made here the half of a tube and then a full tube, putting here the oil, shining the laser here, and then with micrometer going down and measuring actual thickness, and then related this actual thickness to the diameter of the ellipse. So, with all of this said, then we know how to measure. We know how to measure the thickness. Now, this is measured thickness, and here you can see as function of the angle. This is the relative thickness of the film, and these points are what we have measured, and this is the model that we have developed based on also something that was done at ACRC. Evan Hurlbert was a PhD student of Professor Newell. They had developed in 2000 that model, and it shows pretty good results. So we have here experimental values and the model prediction. So we understand now the thickness of the film, and now we are going to droplets. Okay, this is maybe the most interesting to me. This here is the valve, discharge valve of the compressor. It is a reed valve at 35 hertz, compressor running 42 and 50 hertz. So you see now visually how the flow, this is when the valve opens. This is how flow looks like of oil in our case that is really leaving the valve. I have other videos, and it will take us hours and maybe next time to show you how valve goes up and how valve flows and how that oil is breaking and all of that. But here, my objective is to show you that these are not really droplets that are coming out. These are ligaments and droplets, and later all of these ligaments will break. It will break and then turn into the spherical mode due to surface tension, and it will break because of interaction between vapor and oil. And then when we measure here, this is here mass distribution as a function of diameter. So basically we were measuring this diameter of droplets, and these were between here at the discharge, mostly between 100 and 500 microns. That means 0.1 to 0.5 millimeters, most of that. Most of the mass is somewhere here. Most of the mass is somewhere here. This here shows the signal frequency, how these, and these are the speed of all of these droplets in time. So you see that there is always some variation of the average speed, and average speed is presented here with red. So this is how flow looks like at the compressor discharge. I believe you probably haven't seen that so far. To my knowledge, we are the only group that is doing this. Now when we go here, this is also a very nice video. This is the video at the lower velocities of oil flow. This what you see, these are droplets of oil, and this here is a film of oil, and you see how it looks like. From time to time, these are waves that are now relatively large. Here we see droplets. Some of them are absorbed in this film, and some of them bounce off the film. So not all of these droplets are absorbed when they touch the film. And of course, this velocity here was, velocity of vapor was relatively low to be able to get this nice picture. So we haven't seen, you cannot see here oil removing from the crest of the wave, being removed from the crest of the wave. So this is how the discharge looks like. Amazing. So now we can say we maybe know what we are dealing width. But not yet. Why? Because the problem is, when you now want to measure, this is what you see with the camera. This is like saying like a temperature, you know. There is always that saying for the student, you know, when you put a thermometer, you don't measure the temperature that you expect to measure. You measure the temperature of the thermometer. The same is here. We see what camera can show us. Because when you can see this video, if we go back, you see this video, you don't know what is the depth, because look at that. Some of these droplets are very much blurry. They are out of focus. How many of them are out of focus so much that we don't know how much is there? How to determine what is the depth of focus? And when we see this, is this in a 0.1 millimeter slice or maybe 0.5 millimeters? Is this here because our camera, is this here blurry because it is far away or it is closer to us? What is going on? This is now the next step. And whoops. Okay. So this is what you get from the outside, some droplets. Then we have developed various software techniques to eliminate the waves, and then we have here only these droplets. Now we go and enlarge the droplet, and this is how droplet looks like, and all of these numbers here are the grayscale number, and that grayscale goes between 0 and 255. This 255 is only for this camera and for this software, it doesn't matter. So basically, what you see here is what camera sees, because we had to make a software that will do that. So now, you can say here, maybe this is sharp, maybe this is not sharp. And this in the center is kind of shiny part of every ball that you see in the center of every sphere, you see that shiny part. So, with this, we can now say something about that. And this is, oops, again. This is this. First of all, we had to calibrate what we see. So we have taken one bead of glass, so constant known sphere. And that sphere was some of that with all of that at the same time. This is a focal distance, and this is what you see. When it is closer to the camera, this is what you see. And when it is further away from the camera, this is what you see. So now this here is the video image from being in the focus to being out of the focus, and now you need to know what is that in millimeters or in whatever scale you want to use, so that we can now know how much of these droplets are inside. Oops. Now, what is important is to measure, and this is that angle gradient, and when that gradient for these three, green, red, and blue situations, and then when that gradient, if it has a certain value, this is what you see, and this jump in the middle is this shiny dot in the middle of a sphere. So now, when this angle has a certain value, that we know that we captured, this is close to our focal length. So then, with this type of a situation, we can say how certain we are, what is the visual depth of our camera. That is important because with this, we can then determine how many, or what is the density of these droplets inside a certain volume. And then we need to measure oil droplet velocity, which is shown here. And the way how we do that, I have shown you. We go and clean the video, and then we have only droplets here in this form, and there are many steps in between. And then we look into two images. in a known difference of time. And this one time is black and the other moment is red. So now putting vectors between the black and red dot, you can then calculate what is the velocity of that droplet or each of the droplet or velocity in one direction. And then we can plot these velocities and see what is going on, which you have already seen. Now, I'll tell you something about now oil retention and oil in circulation rate. These are the results which are amazingly good. These are extremely good. Let me show you what you can see here. This is here oil retention measurement, and yellow is this here is the film, and the red is drop. And that is a mass of oil retained in a certain volume of that tube. So yellow is the film and red is the drop. For two compressors, typical automotive compressor, this is a swash plate type of a compressor, and scroll compressor that you have seen over there. And typically scrolls are with oil sump, and this is with no oil sump. And you see that really what is happening in the tube is not much of a function of a type of a compressor. So you see here diamond and circle. All of these are somewhere about 0.04 grams in that length. And velocity at a certain velocities that are here in meters per second, between 20 and 25 meters per second of the vapor velocity here. Now, when you look here into what is happening in film and drops, so basically this here is telling you what is OCR. Here we see something around, let's say, 3% or so. So OCR measurements are presented in the same way. This is a contribution of to OCR of droplets, and this is in the film. Please look into this. It was totally different before. This here. Most of the retention is in film, just a little bit in droplets. When you look into OCR, most of the contribution to OCR comes from the droplets, and and very little from the film. So with this, I could come to summary, and sorry I was taking a little bit longer than I should have. Using this non-intrusive method, we can say something about something very, very precisely what is happening in the compressor discharge with the oil. Oil mass is mainly contributed by oil film. Oil mass flow rate is mainly contributed by oil droplets. And there is a considerable velocity difference between vapor, oil droplets, and oil film. This chart here, so this is what you see when you look into the discharge, and it tries to show that as a function of velocity, oil film moves relatively slow, while droplets follow almost with the same slip velocity, follow vapor velocity. So OCR mostly comes from the drops, retention comes mostly from the film. So the point of this presentation was to show you, on one hand, what is the difference between oil in circulation rate and oil retention, that we can measure that, but much more, I wanted to point out that we can characterize now oil flow at the compressor discharge, and the same way in the compressor itself. That will be another presentation, we have done that. But this is more kind of introductory part for this particular moment. If you have time, I'll be glad to answer to any question. If not,
we have no time.
We have no time. Okay.
Hvala gospodinu Hrnjaku. Produžili smo već kasnimo od starta. Ja bih odmah zamolio drugog predavača, gospodina Aleksandra Pačaja.